All right, let's get started. My name is Alex Turner, Program Manager for the Managed Languages team at Microsoft. And these days we're working on all sorts of cool stuff on the Managed Languages team, figuring out how we get our compilers rewritten for Project Roslyn, which you may have heard of. But what I really want to talk about today is the stuff that kind of consumed my life for like the last 2 years, right? And that is the features we shipped in VS 2012 in the VB and C# compilers, specifically the async language support, as well as what we've done for the Windows runtime. It's about 3 years ago at this point that we were trying to figure out from the language side what we could do to actually tame the complexity of doing asynchronous development. It's something, we'll get into a bit exactly what I mean by that, but asynchronous methods, asynchronous APIs, they're out there. They're things you have to go and talk to, but it hasn't always been the simplest to go consume those from our languages. And at the same time we were thinking about that, Windows 8 was sort of in its early stages, and the Windows runtime was being formed. And part of the idea of the Windows runtime was to make it really easy to write asynchronous or to write responsive, actually, client apps. Apps that you interact with them, you're especially on a tablet, you're flicking around, you have full fidelity, you can skip 60 frames a second as you're swiping and scrolling. For that, you really have to make sure you don't block the UI thread, you don't have any hitches there. And so they took a huge bet on their side, on the Windows side, in saying we're going to have a lot of async APIs. So sort of these two forces kind of aligned, right? And it made it important for us to make sure we supported both, right? We had to be a great language for creating Windows Store apps, for you to go and actually consume Windows runtime APIs to do so. But we also needed to make sure that our solution for doing asynchrony really well would work against the Windows runtime. And some of that stuff we were talking about, like, one of the impetuses is Windows 8. We want to make sure that Windows 8 client apps and any other client apps you're writing can stay responsive. The other big reason we want to do this is as people start to push out to the cloud, as you're writing Azure apps, as you're writing apps that want to have this high scalability, you want to get as many users on any given node as possible. And the way you do that is to avoid blocking or consuming any resource more than you need to, right? And threads, it turns out, can become one of those constraining resources. Every thread you have is memory that's allocated for that thread, for the stack. And so if you're actually spinning up a whole bunch of threads, that could become its own performance bottleneck. And so, addressing responsiveness in the client, scalability on the server, this is why people are starting to use asynchronous APIs, and really they're becoming the norm. It's sort of the normal philosophy now that, hey, I'm going to expose something to you. It might return in 1 second, in 10 seconds. Let's say it's a network download. And I'm going to give that to you not as an API that'll block your current thread until that result is available. I'm going to give it to you as an API where you tell me, hey, what do you want to do once that result is done? What do you want me to call into and give the result to? Which method, right? And until then, we're going to go back and we're going to make sure that your thread is clear, that there's nothing on it taking up both the control of the thread, if it's the UI thread, so you can stay responsive, but also on the server, so we're not wasting that response thread. And so as we've started to do async, you see a lot of ad hoc patterns. You see things where you're accepting callbacks or things where you're subscribing to events. These are some of the patterns that we've had up to now. But really, the industry is crystallizing around this future abstraction. And the notion of futures is that you have a first-class representation of some in-flight operation, something that's ongoing that you want to be able to track so you can tell when it's completed, when it ends in an error, and so on. And we have some of these abstractions. We'll see what they are in .NET. You may have seen the task type in .NET 4.0. Well, we're reusing that type to be our modern future abstraction. And so we have .NET Async, which is what we're building on top of for the C# and VB async feature for the await keyword. At the same time, Windows Runtime has created its own future object and its own infrastructure for doing async operations. And there's some differences between them, but they're actually pretty similar. And since sort of the beta of VS 2012, which was the developer preview of Windows 8, those details have been minimized a great deal. And so those worlds are far more similar. I'm going to cover on a few of the remaining differences now as part of this talk. But really, the goal of having this unification has been that you really don't have to think. 95, 99% of the time, you don't have to think about this difference between those two worlds. You're just able to consume them and easily move between them as you want. And so just so we're on the same page talking about what we mean when we say asynchrony. Asynchrony is kind of an overloaded term out there in the industry. It can mean all sorts of things. When we say asynchrony, we mean this idea that you have a method that you call into that returns immediately, even though the operation isn't done. So to see that difference, you look at the top. This is a synchronous call. I have a call to download data. I'm going to pass it some parameters. I'm going to get data back. And then I'm going to take that data. I'm going to process it. I hand it off to another method. Now, when this happens, all right, I have some little blip of work, which is actually kicking off the download. But that download data call isn't going to return until the data is available. So actually, that entire time, my thread is blocked, even though my computer isn't doing anything waiting for the download. It's just sitting there expecting a packet at some point in the future. And only then, once the data is available, can I go call process data. My thread's blocked for that whole time. Now, you look at the asynchronous case. For asynchrony, well, I'm saying download data async, and I'm getting back this future object. And on the future object, I'm calling some method that say continue with, and saying, hey, once you have data, go ahead and do this thing. In this case, I'm saying process data. Call process data, hand off that data you just got back. And so what that means is download data async can return to me right away. I immediately subscribe that continue with handler, and then I move on with whatever else I need to do, maybe returning back to the UI message pump. And so it means that in the interim, before the data is actually back, before I go in and call process data, there's nothing else going on in that thread. The thread is clear. And that means that other UI messages can be handled, right? So you could assume all those little green boxes, those are other touches. Those are the user moving their mouse around, hovering over things that need to change their state in the UI. So I can actually keep the UI responsive. I can keep the UI scrolling if it's on a touch device. And all of that is possible because the UI thread is clear. If I go back to the original synchronous example, all of those UI events that I wanted to have that the user was making can't actually be handled until my download is done because I blocked the UI thread doing that. And I'm sure you've all seen unresponsive apps that you've worked with where you're in the app, you're interacting with it, suddenly it hangs and kind of frosts over, and then when it comes back, all of your UI things you did kind of unqueue, and they go off and they do something maybe you didn't even want to do, right? So it's very important, especially as you're writing Windows Store apps where people have this high expectation of responsiveness, that you keep that UI thread completely clear. The other benefit of having the thread clear is, well, what if I want to go do another parallel operation? You think of environments like Silverlight or in JavaScript in the browser, where there's only one thread where you're even allowed to make network requests, which is that core browser thread that your tab is assigned. And, well, in that case, you better have the UI thread clear, because otherwise you're not going to be able to do a second download until the first download completes, right? And they may be independent. And so, yeah, in the first case, if I wanted to go loop and do another download, I would have to wait till that first one's done, block, do it again. In this case, I can just kick off both requests. I only consume the thread as long as it takes to actually kick off the request, and then I get to move on. And the results can come back. Maybe they come back out of order, but I can process them as they come back in. And so, it looked like we already had this handled. Why do we have to bother doing anything in the language? We already have the ability to make those kind of APIs. Well, you saw it was getting confusing, right? Like, already here, I'm starting to pass in Lambda expressions. My code's getting a little more complex, right? Before I just said, I want to download the data, I want to process the data. And then afterwards, now I'm saying, well, I want to download the data, and then later when the data's done, here's what you want to do with it. And then imagine I wanted to chain some other kind of async operation after that. I wanted to take that, maybe it was a URL, I want to go fetch some more data. Well, now I'd have to, inside my Lambda, have kind of another Lambda, and they'd go off and get nested more and more and more. You end up in this kind of callback hell. The fun thing I've heard, people talk about spaghetti code, when you have a lot of go-tos in code and it's jumping around. The best analogy I've heard for this phenomenon, when you have all the nested lambdas, is macaroni code. You end up with a lot of little independent nuggets of functionality that you're kind of bouncing between, but it becomes hard to then reason about the flow of your program. And so what we're doing now with C# and Visual Basic is saying, let's add support to the language itself to actually let you write your code sequentially, let you actually express the flows, the workflows you want in your methods the way you would in synchronous code. And you get back the ability to use all those advanced control flow constructs, things like if statements and for loops, all those things that become really heinous to actually deal with when you have callbacks that you have to manage and start flattening loops and calling back into yourself and all that kind of stuff. And so let's take a look at an app that's written for Windows Store that uses the Windows runtime, calls into a bunch of its APIs, and actually manages to stay responsive by using await. So I'm going to switch back here. And I have an app. I'm actually going to just run it first so you can see what it does. It's a Windows Store app. It's nothing too beautiful to look at. It's based on one of the default templates. And the idea here is this is an app that builds photo mosaics. So if you haven't seen a photo mosaic, it's the idea that you have some kind of theme for a bunch of little tile images that you're going to pick from. Here are the themes that we have to pick from our different tags for doing searches on Flickr. And so we're going to pick one of those, get a bunch of images, about 1,000. We're going to take those images and figure out how do we lay them out in order to form a mosaic of some larger source image that we're trying to approximate. So you're going to pick the image, you're going to pick the theme, and then it's going to go out and it's going to make some kind of first-order approximation of that thing you chose. So first I'm going to choose, all right, I want to do based on flowers. So I click flower. And now it's asking me, which image do I want to approximate? I know I'm going to build it with flower tiles, but I want it to look like something else. And I'm going to choose this picture of me speaking, I guess, about 4 or 5 years ago at Tech Days Belgium. Kind of epic lighting in the background. And so you saw it was downloading tile images. I'm not going to make you watch me download 1,000 tile images, so most of them were actually already cached. But it's downloading those tile images. It goes on to calculate the mosaic, which is some CPU crunching it does to match which ones fit in which place the best. And it makes something that looks kind of like a tile-based approximation of my face. And so there we go. So now we have this mosaic. And it's a simple app, and you could have seen as it was downloading, if I moved around, I was still able to get hover animations. I was still able to kind of scroll around in the UI. I'm able to do those things because I'm not actually consuming the UI thread while I'm either doing downloads or kicking off background work to other threads. All right, so we'll stop this here. And really the bulk of the logic, that workflow that I wanted to express naturally, is inside this item click handler. This is the core place where I'm going to go do all this work to show the UIs and go through and do my calculations. And if you've done XAML programming before in WPF or Silverlight, a lot of this should just look familiar. If I go up here, you can see I'm pulling in the exact item that was clicked on from my model. I'm going to go pull it in from the item list view, get the model object. And I'm going to say, all right, well, in the model, set the status text to be some text. And that's going to actually data bind back out to the UI and affect the UI. And so I'm saying, all right, we'll tell the user that we're choosing a source image right now. And then here I'm going to say, all right, var picker equals new file open picker. And if I look at what type file open picker is, this is from the namespace windows.storage.pickers. And so because that root namespace is Windows, I can tell this is a Windows runtime API that I'm talking to here. And specifically, it's a picker API. It's one that shows that big full-screen UI to kind of do an open file dialog, the Windows Store equivalent. And so I get that in, and it's a .NET object now at this point that I can handle like any other object. So I'm going here and setting some properties on it, setting the file type filter and saying I want some thumbnail view that I want to display. And then finally, I'm able to call here this pick single file async method. And this is actually going to show the UI on the screen. And if I look here, though, I can tell that this is a special kind of method, that this is one of those asynchronous methods that I'm going to want to deal with especially. So, well, my first clue is that it ends with async, right, in the name. But that's not the only thing. If I hover on it, you can see that the IDE is telling me that this method is awaitable. And so what that means is I have the ability to go await that object. Or the object returned here is going to be that future type, right? I'm going to get back an object that represents that picking operation abstractly, right? And I can then wait on that, figure out when the user's actually done, and get my result back out. In this case, you see the return type is async operation of storage file. And so async operation is the Windows runtime's future type. It's the Windows runtime's future type for an operation that returns a value. And so in this case, the logical return type that it's going to give me back is a storage file. And you see here, I'm using this new await keyword, and what pops out the other end is a storage file. And so I'm calling this API, I'm awaiting it, and then out the other end I actually get my value. And so what does it actually mean? What's going on here when I get to that point and I await? Well, what happens is, I really need, remember before, I need to return out of my method. I need to free up my UI thread while the user's doing this. They might take 10 seconds picking things there, and I can't block the thread while they're doing that. And so what I really need to do, first of all, is return. And so when you get to an await, what happens is the method gets to that point and then returns. But before it returns, what it does is it sets up the rest of the method that you have here as the callback. And it does that for you, so you don't have to think about it, and you don't have to start nesting your method into a bunch of lambdas. So I'm able to just say here, await pick single file async, and under the covers, all the plumbing for asynchronous operations knows that when that picking operation is complete, I want to pick up here where I left off and keep going, and keep all my local variables where they were, and so on. And so I'm able to do that because specifically up here, you see that I have my method marked as an async method. And so having an async method means that I'm able to await inside that method because my method is going to have some compiler plumbing that enables it to be paused and then resumed later, and to have all of that state put back the way it was, all the local variables reinstated, so that my method can continue the way it was. And so I have that await here, and what comes out after I await it is original file, right, which is going to be this storage file. So my future type encoded that it was a future object that had a certain return type awaiting it gives me that back. And I get to keep going, right? So original file is now an object I have. It's a storage file. That's another Windows runtime type. And one of the operations it has here is open async, right? So I can actually now go open that file. It itself is an async operation because the file could be remote, could take a while to load. So I go and I open it, and what it gives me back here, you see, is async operation of irandom access stream. And so when I await it, I get back an irandom access stream. And so I'm naturally able to kick off these operations, pause until those operations are complete, get their values, and then continue doing further operations and just chain them naturally. And my code still looks the way it would if I was just calling these things synchronously and blocking. And so now I have the original stream kind of out here. I take the stream, and what I'm able to do then is, if you've seen XAML before, this is me setting up an image source, and I'm setting that image source into the model. So I can say, all right, well, where I'm going to show a preview of that image that they chose, the image they want to approximate, that picture of my face, let's just put that into the model so we can show that in the UI. And so we set that up. And so now we're going to say, all right, we're done choosing which image we're targeting. Let's actually download all those tile images that the user wanted. And so we say we're downloading the tile images. We go here, we call a helper method that we defined. You can still call your synchronous methods just fine from an async method. That's all right. So I call getFlickerURI. It gets the URI we want to query. And now we're actually going to the network to do the query. We're going to go to Flickr and get back that list of images we want to download. And what I'm using here isn't a Windows Runtime API. HTTP client is actually the new .NET 4.5 HTTP library. It replaces web client. And I'm calling on it, on a new instance of it, getAsync. Right? So I want to go fetch something from the web. That makes sense. But what it returns here, you see, isn't async operation. It returns task of that response message type. And this is because task of T, in this case, task is that .NET future type. So we had async operation, which is what Windows Runtime defines that they use across JavaScript and all their projections, right? But on the .NET side, we have a type, we have task. And you notice I'm getting back task of HTTP response message. I await it, and what comes out the other end is HTTP response message. So it's that same flow. I'm signing myself up as the callback, but I'm able to do so just the same way. I'm able to do so on .NET types, on Windows Runtime types. It's all the same to me on my end. And so I continue on. I have basically the same pattern here. I'm actually reading the string in as async. They have an async method for that, so I await it. What I get back out here is just the raw string. And then I go here, and I'm saying parse photos from XML. This is some crunching I do to figure out, okay, pull it apart, pull apart that XML response I got, figure out the list of images, take that list that I get back, hand it off to fetch images async, right? This is another method I have, but in this case, fetch images async is my own code. This is a helper method that I wrote, but I wrote this as an async method. And we'll see in a sec how to write an async method, but this is a method that is my own helper, but it follows that same pattern, right? It ends with the word async, it shows up as being awaitable, it returns a task. So I can track when my helper method completes. But because it's task, it's able to go take 10 seconds and not block the thread that you called it on. It's able to just notify you when you're done. And so I await that, and what I get back out is that list of storage file. And so I keep going, and I say, all right, here, calculate the mosaic. I call another helper method that I wrote, which does all the CPU crunching now, and say, take the original file, take the tile list, combine them, spit out the mosaic. And finally here, I go and I say, all right, open that image, do the same kind of thing here to set it into the UI, and then finally, I'm done. So I've represented my flow linearly the way that I want to think about it, right? I'm picking the file, I'm downloading the images, I'm calculating the mosaic, and it's all just about me calling methods, some of which are defined in Windows, some of which are defined in .NET, some of which I defined myself. And I'm able to just compose all of those naturally, the way I'd expect when I'm consuming various APIs. All right. Well, so now I can await all of these things the same way. This is helpful, but my method's getting kind of long, partially because I have the font size all jacked up. But I may want to actually shrink this down. There's a bunch of lines in here. Maybe I want to take the act of choosing a source image and make that its own helper method. So let's write another one of those helper methods that you saw me call before. So I'm going to go here. I'm going to select all of this text. This is the code that I want to extract that's going to do the choosing of the source image. And if we look at this code in terms of the stuff that you'd actually need afterwards, the stuff I would need beyond this, the only thing I really need is this original file, right? That's the thing I'm choosing. If I select this, I can see that down here, it's used here inside the code I was selecting, but it's also used down here. When I actually create the mosaic, I need to remember which file it was that I selected. And so whatever method we make, we're going to have to make sure that we return something of that type, right? This is going to give me back storage file. So we're going to write a method that's going to have to logically give us back a storage file. So let's actually just select all this code here. And I'm going to right-click. I'm going to use the extract method refactoring, so I don't have to do this myself. I say extract method, and I'm going to call this choose source image async. And you see I hit enter, and what it created was an async method. It made me an async method. If I take a look, I can hit F12 to jump into it. It made me a method that was marked async, which it has to be because we extracted some code that had awaits in it. But importantly also, it returns task of storage file. Remember, we wanted to get back out a storage file, but I can't just return a storage file because I'm not going to have one until the user's done, until all these awaits are complete. It's too late at that point for me to return a storage file. And so I return this wrapped version, this task of storage file, a future that says, hey, eventually I'm going to have a storage file to give you. But for now, here's this object you can use to track when that's going to be done. So I return my task of storage file, but how does it actually get returned? This is a method that I wrote. I don't have anything here that's creating tasks. Well, remember that flow from before. You come through, when you get to the first await, you return, right? And before, when we did that, remember up here, this method was async void, right? This method we started with was a void method. And it has to be because it's an event handler, right? And the signature for the item click event returns void. But the method I just made isn't. And let's see what happens there. When someone clicks, code's going to kind of start going through here. I'm going to get to choose source image async. I'm going to await that, which means I'm going to return. But before I do that, I actually have to resolve this expression. I have to resolve what it is I'm awaiting. And so the compiler, the control flow is actually going to go into here. I'm going to go on. I'm going to make this file open picker object. We're going to call picker.pick single file async. This is that Windows runtime method. And it's going to give me back the operation that says, OK, eventually here you'll have a storage file. And then I await that. And so the act of awaiting this, remember, what does await mean? It means I return. And so I return from choose source image async. And so we come all the way back up here. And that means that, we returned from here. But what did we return? We returned the task of storage file. That was an async method, so it returns its own task. So that's what happens. When you get to that first await inside your async method, you immediately return, and you give back the task of storage file. The plumbing that the compiler generates for you makes that task for you. And it gives back a task. It says, well, we don't have a storage file yet. We didn't get to the end of the method. But we do have this promise that in the future you're going to have one. And so that's what's returned here. And then I immediately await that. And so because I'm awaiting something that's not done, this method returns. And so this is going to return out to whoever called item click, which is going to be that XAML message pump. And so we're going to keep going then, and the UI thread is now free. And maybe 10 seconds later, after the person chooses it, eventually, hey, that original implementation here, the pick single file async, this operation is now complete. Somebody picked the file, so picking is complete, which means that the callback that was signed up is triggered. And so the callback is going to be, as we expect, the rest of this method. All of this stuff is now going to start executing after we unpack that original file out into its own variable, right? So the await does two things. It pauses your method and returns back, right? And then upon resuming, it takes the result value, the logical result, out of that operation object, out of the future object, and assigns it as the value of that expression. So I can assign it out here. And then I can continue going here. And I do actually another await, right? So I'm doing an await. I'm awaiting open async. I pause. I wait for that to be done. I resume right here. And then I continue going. And down here at the bottom, I have a return statement, right? And I'm returning original file. And original file, its type is storage file. But the physical return type that I have for my method is task of storage file. But that's OK. So sort of like yield return doesn't actually represent, IEnumerable when you have iterators there. It's the same idea here. Return statements and async methods are about the logical return type. In this case, I'm logically going to return storage file. That's what my task should actually have as its value. But I'm not going to return it from my method. My method's already complete. What I'm going to do is now, when I get to this line, I'm going to go to that task and say, hey, here's your result. I'm going to call set result on the task. The compiler does this for me. It calls setResult and says, here's the result of the task. And by the way, you're now completed. So take anybody who was waiting on you, who had awaited you, who had their own callbacks hooked up to this method's return value, and let them continue. So the moment I say return here, this method up here now wakes up, because the task of storage file that it was awaiting now has its storage file. So we're able to continue going inside this method. And so that's that kind of natural way that I can now compose, not just over Windows runtime methods and .NET methods, but also the async methods that I create. And I can go back and I can call them. Now, one thing to note, you saw me here, I'm awaiting something from the Windows runtime. I could await .NET things. The thing I return, the return value I have always has to be task of storage file. So when you make an async method, your return type is special. It has to be that one type, either task of some T if you're going to return a value, or just plain task if you want to just signal completion, right? But the things that I can await can be broader. And so it's just important to know that distinction. All right, well, so now I have my helper method broken out. And what I want to do is make this a little more robust. Now, right now everything seems to be working great, but we know that when we're operating against network APIs and other APIs that can be latent, they can also fail. There could be a network delay loading from the disk. There could be a disk error. Someone could disconnect a device. And so we want to add exception handling to the system. But we want it to work no matter where the exception is coming from. Like, for example, the exception might come from our async helper method here, choose source image async. And there's various places it could come from. It could come from OpenAsync here if there was some disk error. It could come from pick single file async if there's an issue actually showing the picker. And one of the issues you can have with a picker, this is just a Windows 8 tip, if you make one of these picker types, the ones that are doing files, you have to actually specify a file type filter. You have to tell it what kind of files to show, even if it's star to show everything. And so if I comment out this file type filter property, meaning I never set it, then it's going to be an exception when I go down here and call pick single file async. So now this is going to cause an error that we might want to deal with. But the error doesn't surface exactly the same way, right? Like most methods, when you call them, that method itself, the act of calling it goes in, the exception bubbles out from where it came from. But with async methods, what you typically get is that the exception doesn't come when you call it. The exception comes later when you await it. Because the exceptions that this method is going to produce aren't just surfaced back. The exception might come far later after the user's interacted with something. Maybe not in this case, but for many exceptions it would be. So I need to actually just signal to the people who are awaiting me, hey, by the way, you were waiting for a result. Sorry, there's not going to be a result because there was an exception. And that's another state that a future object can end in. Future objects can be successful, or they can have an exception. They can end in the accepted state. And so it's not the act of calling this that's going to throw the exception. It's the act of awaiting it. So when I await this async operation, I realize eventually, oh, there's an exception that's being given to me. What does an await do when it gets an exception? Well, it throws it, rethrows the exception. Just like it returns the value to the thing you're assigning to when you get a result, it rethrows the exceptions. You can resurface it in the method that's doing the await. And it's rethrown, but I don't actually want to deal with it here, right? I really want to deal with it in my calling method. I want to deal with it in my main flow so I can handle all exceptions the same way. And I don't actually have to write any code here in order to do that. So the await makes sure that my exceptions are automatically resurfaced. But the code gen, the stuff we actually emit into this method for doing an async method, makes sure that those exceptions are also recaptured and put into that task of storage file. And so just like this async operation ended in an accepted state, now my task of storage file is going to capture that exception, and it's going to end in an accepted state. And so now when I scroll back here, you see I'm awaiting choose source image async. Well, the act of awaiting that task that ended in an accepted state does precisely the same thing. It's going to rethrow that exception and continue bubbling out to the logical callers, the awaiters for that method. And so I'm saying, all right, await this. This is going to throw an exception. It's going to bubble out. Now I want to deal with it here. How do I deal with it? I just write a try-catch block. So I say, all right, we'll try, and then take all this code, this too, and I'm going to just say here catch exception because I don't have anything that intelligent to do. I just want to report it. And I'm going to say, oops, an error occurred. And so I've done that, and now you can see, oh, actually, yeah, we have the exception in place, so I'm going to run this now. And the act of clicking flower now causes an exception while it's trying to show the picker, and so we get, oops, an error occurred. And it was able to do this across all those different layers. It's cool to think about what's happening here. I called pick single file async, which is that Windows runtime method. it gave me back a future object which ended in the accepted state. The act of awaiting it rethrew that exception. My task, my .NET future, captured that exception. Then out in my outer method, the .NET future object was awaited, and then it rethrew the exception, and then it was caught naturally by my try-catch. And so exceptions can flow through Windows runtime futures and also through .NET futures, and I'm able to just write a try-catch in the place that I want to write it. If you've done async exception handling today in these kind of callback models, you know that very quickly, especially if you're trying to compose or make APIs, it becomes a headache to consider all the different places an error could occur. The error could surface synchronously from the call, or it could be given back to you in your callback, or you could get like an error object in the callback result that might be telling you something, and then you want to filter all those to the same place, then you make some other method that handles the exceptions, and it quickly falls off the rails for you to actually write a reasonable program. So much of your program becomes plumbing around all the exceptions that might occur and getting them to the right place. For one of the patterns, if you've ever seen kind of begin and end methods, like begin read and end read, if you want to implement those methods and you actually want to handle, or call into those methods, and you want to handle all exceptions exactly where they could go, like, an exception could come from begin read or from end read, and if it comes, I have to make sure things weren't executing synchronously. We wrote it out. It turns out a 100% correct implementation is about 70 lines of code. And probably nobody here, including me, has ever written 70 lines of code when calling those methods. So we're leaving places where stuff can leak out and you can get unexpected behavior. And so the idea is to really return you back to something known, something that's as simple as what you intend, right? I want to call all this stuff. If any of these things go wrong, handle it here. So you get to express your logical intent, and that intent is then captured and actually becomes what happens because we have all of this flowing through the future objects. And so that's one thing we can do. We can handle error cases in that way. What you may have noticed, though, is that every time I'm calling one of these async methods, I'm getting back a future object, but I'm immediately awaiting it. It's not too interesting that I'm getting an object if I always just immediately take that object, shove it off, and await it and forget about the object, right? There's got to be more I can do by having these as first-class objects. And so, the first thing I can do is actually capture the object so I can hold on to it. So if we take a look at my helper, you see it returns choose source image async, it returns task of storage file. Well, if I just skip the await, I can now get back the task of storage file. I'm not awaiting it, so I just get back the raw task and I hold on to it. And I renamed my variable to original file task. I can now go here and say var original file equals await original file task. And so that's not very interesting. I just separated it onto two lines and made an intermediate variable. But what it means now is I can actually do other things with this line of code. If I take a look, original file, where is this used? I notice the first time it's used is all the way down there. It's used when I'm creating the mosaic. I don't actually need to know which file the user is choosing to approximate in order to download the tile images. They already clicked something that said flower. I don't care which image they pick, right? And so at that point, why am I actually blocking here? I could already be downloading the images. And so you can imagine coming up with a parallel thing and saying, okay, I have two methods, I'm going to do two tasks, and one's going to download, and one's going to do this. But we don't actually have to even be that explicit. All we have to do is ensure that we push this await as far down in my method as possible until the point when I really do have to wait for that thing to be available. And so you see now, I'm calling choose source image async, which is going to go actually show the UI. But while the UI is shown, all of this stuff is going to go. All of the downloading code to download those 1,000 tile images is going to run in the background. But this is still here, right? This is at the end, right? And only at the end, once all the images are downloaded, do I then say, well, let's see if the original file has been chosen yet. If so, keep going. If not, let's hold on until it is. And I'm able to do that even though all of this code is still running on the UI thread. It's not being put off to background threads. It's just making better use of that one UI thread that I have. And that's one of those critical things that's important to know about await. Every time I get to an await, I'm being put back into that same context, that same threading context, where I left off, right? And it's critical because some of the stuff I'm going to do here is going to be about setting XAML images, right? And that requires me to be on the UI thread to do that. And so every time I say await here, it's going to go do this operation and then put me back onto the UI thread. And I say await again, and it puts me back onto the UI thread. It makes sure that I'm actually in the place where I expect to be. So I don't have to worry about how that method is implemented or if it's going to leave me in a strange place. And I know I'm always going to be back in the place where I started. So, okay, well, we've separated this out now. And if I run this, one of the things we can see, if I click flower, let's actually get rid of our error here. it comes up here, right? And you saw downloading tile images quickly for a split second there. But now I'm here, right? And it's trying to download those images that aren't cached. I can, mess around here, sort my single image by date instead. Choose the image and go to open. And you notice the moment I go to open, it instantly goes to calculating Mosaic because it was doing that stuff in the background. So my app is now much faster. And yeah, and again, I didn't have to think about how am I going to parallelize this? How am I going to move this into parallel flows? I just moved when I care about what the original file is later in my method. And if you think about synchronous methods, you're always kind of tying when I kick off doing an operation with where I care about getting its result back out. Those are the same place. And one of the benefits you get when you're doing latent async operations is you can separate those two concepts from each other. So the same thing that we're doing here, this is against a .NET task, right? I was able to hold on to it and do it later. The same thing can work for a Windows runtime task as well, including the ones that we have inside here. So pick single file async. This is, again, returning me that future object. I could want to hold on to it. And so I'm going to get rid of the await. I'm going to do the same thing. I say original file. In this case, I'm going to call it operation, since I'm getting back an operation object. That's what they call it in Windows runtime. And I'm going to say var original file equals await original file operation. Now, I can't do the same trick, again, of moving this line down, because you see I need it on the very next line. But it means I can now start to do extra stuff in here, right? So imagine I had some sort of work to do here. I'm going to simulate that work with something called task.delay. Task.delay basically just pauses what your code is doing for 5 seconds. It frees up this thread, right, for 5 seconds. But it does so, yeah, without blocking the thread, right? So it's going to use a timer or whatever it has to get control back to me after that much time while letting other people use that thread. And so I'm going to do it for 5 seconds here. We're just going to say this simulates very important work, maybe some sort of downloads or something. And if I set a breakpoint here and step through, we can actually get a sense of what's going on with this kind of interweaving. If I choose flower, now I step again over pick single file async, and you see when I alt-tab, we still didn't show the single file picker. That's because the UI thread still hasn't had a chance to pump, right? I'm still the single guy in control of the UI thread. But when I go here to await task.delay, now we're freeing up the UI thread, and so the picker shows up, and I can go here, and I can pull down little menus and play with the screen, but then after 5 seconds, control goes on in this method, right? In the background, on the UI thread, these messages are being handled, including my mouse moves, as well as resuming this code here. And so now I go here, I say, all right, well, now I do care. I care about what the original file is, so go ahead and continue there. And so now my code is here. I finally select the image. I say open, and then code continues, right? So you get that sort of implicit parallelization, again, by separating that idea of when you kick stuff off by when you actually finally await it, when you need the result. One final thing to show here, we have this idea, we call it hot tasks, or hot async. You might hear us use this term. And what this means is, I'm calling this method, I'm calling pick single file async. It gives me back an operation. That operation is already running, right? I get this back, I don't have to go call .start or any sort of kickoff method on the future type itself. I know that the moment I call an API, that operation is already in flight. I just have to monitor it to find out when it's done. There was previously, when we had the beta version of, for Windows 8, we had the developer preview, we had VS Beta, we were going and saying, all right, well, maybe this is going to be cold. On the Windows side, it was a cold async, right? And you had to get it back and you had to start it. It was just a different choice in how the implementation worked. But it meant that there was more of these kind of impedance mismatches. You had to actually start the operation after you signed up the callback, which meant that you couldn't kind of be as loose with when you did that. And so what we offered was a method here called start as task. And this would say, hey, if you want to get a real task object back so you can kind of await it multiple times, other things you couldn't do, you can get back a real task object. We'll see in a sec on the slide that we've kind of eliminated most of those differences, so you don't actually usually need this. And because they're already started, we don't call it start as task anymore. But there are still a handful of cases where you do want to get a real task object, a .NET task object, that wraps that underlying Windows RT future. And so in that case, you can call as task. And you see it's pretty simple. In this case, I had an async operation of storage file. When I call as task, I get a task of storage file, right? So it just turns it into something, and you notice it didn't even change what my code did. It still compiles because I'm still able to await that task and get out the object. It works the same way. But if there's a case where I really need that task object, this is what lets me get a hold of it. And so we'll see how that becomes useful in a sec. So go back to the slides. And what we've seen here is that if you want your methods to be asynchronous, right, the easiest way to do that now is going to be putting on that async modifier. The async modifier takes your method, it turns it into, under the covers, a state machine that knows how to pause and resume. It operates in much the way that an iterator does, being able to yield and then have control come back and produce more values. It does it all behind the scenes, though. What you get to think about is the logical control flow of the method you're producing. You don't have to sit there and make callbacks anymore. In your async method, at the point where you say await, that's where, under the covers, the compiler is going to capture the rest of the method logically as a callback. And in the cases we saw, maybe you could imagine it's kind of just chaining them linearly, like you might do if you had 7 levels of nested lambdas. But it actually is doing something even more fancy, because if you, let's say, had a for loop or an if statement or some place where, well, how do I capture the rest of a method when I'm in the last half of a for loop? Well, we, by doing that state machine trick, are able to resume where we left off and kind of jump back into the for loop and put all your local variables back the way they were. And so we can do those tricks so that you don't have to think about it, and you can await basically anywhere inside of an async method. And so you can think of the things that you're able to await on, these future objects. We sometimes call them awaitables. And on the .NET side, we have 2 of them. We have task, and we have task of t-result. And that's based on whether you, in the task case, don't have a result, or whether you do actually have some logical result type. When you await something that doesn't have a result, you're just waiting for it to finish. On the Windows runtime side, there's equivalent types, right? So there's async operation of t-result. That's the one we saw. That's the one where you await the object, and it gives you back a value eventually. There's also async action, which is the same idea, where I want to await it, I want to know when it's complete, but maybe it just has some side effect, and I just care when it's done. And so you get these back from different APIs, but there were differences. Back at the Windows 8 developer preview, there were differences between them, right? On the async action, async operations side, you had to actually start them manually. And we paved over that for you when you would await. So if you'd await, we'd go ahead and start it for you, so you didn't have to worry about it. But there was a limit to how much we could do there. Like, if it was already started, it was now too late for us to sign up a callback, and so we couldn't await it again. So you had to be very careful that you would only await your Windows runtime objects once, right? And that made it harder to do more advanced control flow, because you had to be a bit paranoid about when you were actually awaiting things. It also meant that you had to think about calling start as task. Remember in that example, I would have had to call start as task to get my kind of implicit parallelization to work, because if I didn't actually kick off the operation, it wouldn't have been going yet. And there were subtle bugs that you could easily introduce into your code like that. So since the developer preview, we've paved over these differences. We worked with the Windows team, and now inside Windows itself, there is a hot async model. The act of calling a Windows runtime API gives you back a future object that represents an already running operation. And so because it's already running, you can now do all the same things. You can await that operation directly. You can await it multiple times if you want, because we can easily just subscribe callbacks. And if they're already complete, it's just going to call your callback instantly. You can store that object directly and just await it later, like we did inside choose-source image async. And that was fine, because it's treated just the same as we would treat a task. Or the one extra thing you can do, if you really do want a task, you could just convert it to a task using the asTask method. Then you can await that task later. And we'll see some reasons why you would do that. We also saw 2 different kinds of async methods. So there's the async helper method that I created. That was an async method that returned a task. In our case, it was a task of storage file. And so this is the most of the async methods you write are probably going to be async task methods, right? These are methods that can be awaited. They give control to the guy who calls you to say, all right, well, you called me, and now you can find out when I'm complete. You can find out when I throw an exception. It gives you a handle into the operation that's ongoing. It lets you really delegate asynchronous work out back into your threading context. But there's places where you have to have void methods, right? Think of an event handler. We had item click, right? Think of any click, any kind of event handler, any UI in a server that happens to have event-based programming model. This is a place where something's going to be triggered, and it has a void signature. The events typically will have a void return value, and there's nothing you can do about that. And so what we also offer is this ability to make an async void method. But you really want to limit your use of async void methods to the places where you're trying to fulfill those kind of event signatures, or let's say you're overriding a void method in some base class. Because you can't await them. You can't find out later when it failed, what happened, right? There's no hook for you to get an exception. If something goes wrong in that operation, it better internally handle the error that it had, or else it's going to kind of randomly be posted. It's like an unhandled exception handler, and it's going to be harder to keep track of that. So we think of async void methods as these kind of fire and forget methods. It's something you kick off, but then you don't really care what happens to it afterwards. And you can think of events typically that way, especially in a UI stack, right? the XAML message pump says, oh, somebody clicked on this item. But then the XAML message pump really could care less what you do with that information. You're going to go off, do some stuff, trigger some async operations, come back, twiddle the UI, but the XAML message pump is just still going. All it cares is when it gets control again, so it can go call some other thing. And so for those kind of fire and forget scenarios, async void can be helpful. But you really want to limit it there so you don't introduce subtle bugs. So you have async task methods. They're giving you back tasks. And they are these first-class objects that you can interact with. And we saw a bit of what you can do by actually holding off where you await. But there are higher-level things that you can do with these objects, right? Like you think of link, where you get back IEnumerable from all of these different methods. But we gave you where, we gave you select, and all these kind of combinators that operate on top of IEnumerable. IEnumerable is that currency, and there's a rich API that gets built up around that. There's the same kind of thing now around tasks. You have this first-class notion of something that's ongoing, but then there's methods that can take those tasks and operate on them to compose them in unique ways. And so I'm going to take a look at some of those right now. Let's get rid of this breakpoint, and we'll get rid of our very important work here. I guess it wasn't that important. And we come back to our main method. This is where we're doing all the downloading. This is where we're calculating the mosaic. And let's take a look at something here. Perhaps parse photos from XML. This is something that's going to be CPU-bound work. And you see that right now it's a synchronous method that I'm calling. And probably that's going to return pretty quickly. It's parsing a pretty small result. But let's say I actually do some profiling. And I find out this is taking a lot of time, maybe on low-powered devices, maybe because I'm asking for a lot of results and Flickr's giving me back a big XML thing that I have to parse. Who knows? But let's say I decide I want to push this work off onto a background thread. Well, typically if you think of how you would push work to a background thread, you'd probably put the whole operation on a background thread. You'd use thread start, you'd set that up. And then when you're actually running there, every time you wanted to update the UI, you'd say dispatcher.invoke. And you'd put some code back to go, hey, run this on the UI thread so you could do this. Okay, now we're back to the code again. We're going to say, okay, we're going to be in a background thread. Oops, I changed something, go back, update the UI. And you're constantly having all these lambdas that are pushing you back and forth between those two environments. And what we found is a lot of the times, the little blip of code you need to do in the background thread is tinier than all of the UI manipulation that you're doing in your kind of process management, right? And in this workflow management, much of the stuff we're doing here isn't long-running because it relies on other machines. Hey, download this file or do some kind of operation that doesn't rely on my machine doing a bunch of work. And so I want to do most of the work on the UI thread and keep my code simple, but I want to take this part of the code and send it off. And so we gave you a new method now, task.run, that makes it really simple and quick to do that. And so I can go here, put task.run in, and also await it. And now I've created a little lambda that says, all right, well, go off into the thread pool on a background thread. This time it really is a background thread. And I'm going to say, on a background thread, run this code. And the code is going to do the same thing I did before, but it's going to take this return value. In this case, you see it returns ilist of photo info. That's my helper method I called. And we're calling task.run. And it accepts this lambda. And what it returns, you see here, is a task of ilist of photo info. And it's now awaitable. And then the act of awaiting it here pulls it back out, and I get an ilist of photo info. So I kind of plumbed it through this task machinery. But the benefit of that is I've now shoved this little bit of work off onto the background thread. But I get to stay on the UI thread, and I get to think of my control flow the same way I did before. Like I'm awaiting .NET APIs. I'm awaiting, here, Windows RT APIs. I'm awaiting my own helper methods, but now I'm actually awaiting myself putting work onto a background thread. That becomes another thing that I can just await naturally in my control flow, in my normal workflow where I'm establishing what's going on in what sequence. And I get this back out. And so I was able to just take that and segregate it out there. And I can do the same thing for any amount of code, right? This is using a simple expression lambda. But I can go here, right, and I can say, well, return. Let's fix this up here. And so I can say return, and I can turn that expression lambda into a statement lambda. Right now it does the same thing. But I could now do other work in here. In fact, I could say await task.delay 5,000. Maybe I'll do my very important work over here. Right? But what this is now going to say is the await operator can only be used inside an async lambda expression. And so what I can now do is change this lambda to be async. So it's not just methods that can be async, it's also lambda expressions, which are these little anonymous methods you're creating. Those can be async as well. And what that means is with the work that's going to go to the background thread itself can be pausing and resuming. naturally, right? And for this period here where this 5 seconds of work is happening, I'm not consuming that background thread. It's better than me just saying thread.sleep. I could say that now because I'm in the background. I'm not going to freeze the UI. But I would still rather be a good citizen of the thread pool. I want to free up the thread pool for those 5 seconds so that somebody else can go use the thread, some other part of my app that's doing something in the thread pool. I don't start spinning up more and more and more threads and increase my memory usage. And so this would work, and I can now do that. I'm going to actually undo this, put it back kind of the way we had it, but I'll keep this here. And so this is task.run, right? I mean, this is me taking a Lambda and creating a task, right? It's not really combining tasks yet. I'm still just kind of producing them. But one of the things I can do, you may have seen us use task.whenAll in other talks we've had, right? Task.whenAll is a method that combines different tasks into kind of an aggregate task. So if I call task.whenAll, I can give it 2, 5, 10 tasks, and it's going to give me back one meta task that's going to go say, hey, when all of those tasks are complete, then I'm going to complete. And it's going to give me back an array of all the results. And so I'm not going to show that here. I'm going to show actually a different one, task.whenAny, which does a similar thing. It's going to take a set of tasks and complete. It's going to give me back a task that completes when one of those tasks is done. Whichever one happens to complete first is going to return control to me. There's all kinds of interesting things that you can do with task.whenAny to build up more advanced control structures. We're going to use it here to implement a soft timeout. And so you saw that eventually it says calculating mosaic. It just says calculating mosaic there. It takes a few seconds. Like this is a beefier machine. You could have like a tablet or something with less power. Maybe it would take 10, 15, 20 seconds. Maybe you chose a large source image or you have a whole bunch of tile images or something, right? If it's going to take a while, maybe you want to alert the user of that. And so let's say that if it takes more than 2.5 seconds in our case, in order to complete, let's show a message that says still calculating so the user knows that that's going on. So the first thing I'm going to do is separate out this into 2 parts. I'm going to say var mosaic task equals, here, create mosaic async. And I'm going to say var mosaic equals await mosaic task. So I've separated this onto 2 lines again. And one of the things I'm going to do now, though, in between, I'm going to create a delay task. And this is going to be for, let's just say, 2,500 milliseconds. And in this case, this isn't some fake thing that's simulating work. This is actually a delay. I really want to do a delay because that's going to power my timeout. And now what I want to do is I want to say, all right, we've kicked both of these things off. Both of them are now running. Remember, we have hot async. And so create mosaic async is creating the mosaic. And task.delay is waiting its 2.5 seconds. So I want to see which one completes first. So I can actually say here, task.whenAny, mosaic task and delay task. And that's going to go off and come back when any of them are done. But I can now say var first task equals here. And so we're going to wait till one of these finishes, and the first one that finishes is going to be returned. And you can see that's because the return value of whenAny is task of task. Now, it sounds weird, but it makes sense, right, when you look at it the way all the other methods are. The outer task is just the fact that I'm calling an async method. It's task of the logical return value, right? So when I await it, I get that logical return value. But in this case, what whenAny gives me is a hold of which of the tasks I gave it was that first one to complete, which is the one that triggered it to signal completion and return control back to me. And so the actual logical return value is itself some other task. And so it's going to tell me that. It's going to tell me which of these completed. And that's going to be assigned here to first task. Well, we're passing these task objects around. We're using the fact that they're first-class objects. What else can you do with a first-class object in .NET? Well, you can compare it to test for reference equality. So I say, well, if the first task that completed happens to be the delay task, then we know that, well, the delay finished and the mosaic is still calculating. So we want to now go alert the user. I'm going to say here model.status text equals, and I'm going to say still calculating. And that's it. And now down here, I'm able to say await mosaic task, right? And I don't have to worry about whether mosaic task was the first or the second to complete. Maybe it's already complete. If I await something that's already complete, I synchronously pull out its return value. I don't even have to await and go anywhere. We're able to just get that efficiently without wasting time scheduling something. And so I just write my code the same way, no matter which one is going to happen. And that's it. So now if I run my code here, click on flower, pick an image, I hit open, it's downloading, it's calculating, and uh-oh, did it go too fast here? Oh, I forgot to await this. That's the danger with task of task. It's no longer a compile error when you forget to await it. So I'm calculating the mosaic here. Now it says still calculating. And so now we have that extra logic. And you could imagine taking that little bit of code that we did, right, to just have this delay task, and you could encapsulate that into some kind of soft timeout method that you were to create, right? You can start to build up these kind of combinators yourself, these helper methods that you have that can operate on tasks that give you extra capabilities, right? Because it's not all one-off hacks, it's not all different things with different parameters from APIs. You have a first-class notion of a task, and you can abstract over it, and then this method you write is actually going to work for all the tasks that you have. And so we did that here. Well, let's say we wanted to do a similar kind of soft timeout here for the winRT operation. I'm not going to make you watch me do all that stuff again, but I'll point out that when we called task.whenAny, the parameters that it took were actual task objects, right? And this is where you start to get to, well, maybe this is why I want to call as task, right? Instead of just awaiting it directly, I want to call as task, get a real task object. It's so you can pass it to these combinators that are either the ones we define or the ones that you build that operate on task objects. And so I'd be able to then say, all right, original file operation, I converted it to a task, now it's a task. And I could pass that to task.whenAny. All right. And, yeah. And so one of the benefits also, like we talked about before, like the fact that I can await this multiple times. The fact that I can await things multiple times, now even here in Windows runtime, because I didn't have to say start as task to do it, right? I didn't have to convert it to a task. I could have awaited it multiple times anyway. But so that benefit isn't there, but I still have the fact that I can do as task here. So the task object really is this idea. It's this idea that I can coordinate activities in an abstract way. I can get this object that lets me think about anything that I happen to be caring about that's ongoing, that's going to give me a result. Maybe it doesn't give me a result. But I can think of it in this abstract way, and I can reason over it. I can say task.whenAll. I can define my own soft timeout helpers. And I can do those things no matter where they came from. Even if they came from Windows runtime, I can easily call that as task method now. It's already started. I get a task, and now I can handle it in just the same way across both those worlds. And we saw some of these. We saw task.delay. One we didn't see was task.yield. Let's say you're on the UI thread. You've been doing work for a while. Remember, between awaits, you have complete control of the UI. Let's say I want to yield control so that something else can pump so I can actually have some updates. I'm able to say await task.yield to do that. We saw task.run. I can push work off into the thread pool and then await it on the way back out. And I don't have to invert my code. I don't have to make code that's kind of very background thread focused and do dispatcher.invoke to get back in. I'm able to just directly await this background work, this little blip of background work, and then continue on with my UI-focused workflow. I'm also able to compose over tasks. So, we saw task.whenAny. It returns me back that first task. Task.whenAll is, you see here, var results. It's going to give me back an array of the results from all the different tasks that I'm awaiting. And so we saw ways that I could work over tasks. We saw the ways that I could, generate new tasks and combine them. But there's sort of one more thing you want to do with these operations that are going on, and that's interact with them while they're in flight, to actually modify them. And so one of the scenarios we have for doing that is cancellation. And so you imagine I have some operation, it's ongoing, and I want to say, the user hit a cancel button, or maybe too much time has elapsed, and I want to say, after 5 seconds, actually cancel it. Don't just wait for it to go. Do a hard timeout and make it stop. Or maybe the user navigates to a different page or so on. And I know I just don't want to do something anymore. And so I want to be able to trigger cancellation and send that notification into the operation that I have ongoing. And so let's see what we do now for cancellation. What we really want for cancellation is something that's going to let us abstract over cancellation no matter what operation happens to be in flight at the current time. Right? There's APIs that you could call into, and you've seen APIs that maybe have some sort of cancel method on them directly. But the problem with those APIs is I would have to know that this is the current code that's running. If I happen to be calculating this at this time, then I want to cancel that. If I happen to be downloading a file, then I want to cancel that download, and so on. And I would have to then start doing a lot of bookkeeping to keep track of what my current operation is. So what I really want to do is say, hey, no matter what operation is in flight right now, go ahead and cancel that. And so luckily, this task type that we built on, this is that core currency type. It's the one that was introduced in .NET 4.0 originally to power the task parallel library. And they were doing a lot of parallelism there when you're calculating a bunch of stuff, a lot of CPU-bound parallelism. And there you're kicking off lots of work items that themselves kick off more work items. It's the same kind of idea. I don't know exactly what's been kicked off or what might be active right now, but if I know I want to cancel, I know I want to cancel anything that's currently running. And so they already introduced this abstraction over cancellation called cancellation token. And the idea of a cancellation token is I create this one object, and I hand it off to some API method that I'm calling. And that API method now has a hold of an object that I can use to tell it when I want to trigger cancellation. And if it goes on to call nested operations, like maybe I call it and it makes a download, it can hand off that cancellation token to the download. And then basically from this one source, all the operations that are ongoing, that are based off of that source, have a hold of this cancellation token. They can all subscribe to find out when cancellation is requested. And then on my end, I'm the guy who started all this, I can decide to trigger cancellation. And then it doesn't matter what's going on, everybody is notified that cancellation should be triggered, an exception is thrown, and it bubbles all the way back out. And so let's go ahead and actually start implementing this. We'll see, well, where do we want to cancel? What's the most important thing here for us to be able to cancel? Well, the thing we want to cancel probably is that create mosaic, right? It doesn't take too long to do a lot of the other things, but creating the mosaic, that could end up taking 5, 10, 15 seconds, depending on the speed of my machine. And, stop this here. If I go in here, you see that there's a cancellation token that's accepted as a parameter for create mosaic async. This is the general pattern that you implement. If you care about cancellation, you accept a cancellation token. And so I want to get one, but I'm going to need a hold of one. Well, the way you get a cancellation token is through a cancellation token source, which makes sense on some level. And what I'm going to do here, I'm going to put that at class level. We'll see why in a sec. And when I kick off this operation, this logical workflow of you clicking on an item, I'm going to go make a new cancellation token source. And then down here, when we're all done, I'm going to set it back to null. And so now I have this source, and I can produce tokens from this source and actually hand them out, right? And you see here that when I need to pass a cancellation token, I'm able to do so by just saying cts.token. And this gets out from the source that cancellation token object. So the reason these are separated out as two different objects rather than you just saying new cancellation token is precisely for that reason. I'm going to be giving this cancellation token to someone, they're going to give it to other people, and there could be many references to that one object that would be all around the world, right? I don't want any of those people to be able to say, I want to trigger cancellation for some other thing that happens to be sharing the same token. I want to hold on to my own private ability to cancel, which is on that source object. But I'm going to give out the token to everybody else. So I like to think of the cancellation token as being this light bulb that signals cancellation, whereas the cancellation token source is that big red button that you can hit, the one you keep for yourself that tells everyone else that cancellation is requested. So I have CTS token here. There's some other things here that I might as well pass this to because they could be running. They might be the thing that's active when the user wants to cancel. And so one of those is fetching the images, and luckily we have a parameter in that method too. But it's not just my helper methods that have these things. This is getAsync. This is the built-in HTTP client get method for doing HTTP gets. But we see there's another overload. There's one overload that takes a cancellation token. And so I can pass this here also. And so that could be canceled if that was the thing that was ongoing. And so the one last thing I want to do is I want to be able to pass this to my choose_source_image_async function. But we don't have that parameter yet. So let's go ahead and add it and see what that involves. I'm going to go up here. I'm going to accept a parameter of type cancellation token. I'm going to call it cancel. And I'm actually going to make it optional. I'm just going to say default of cancellation is the default. Now, the reason I can do this is because cancellation token is a struct. And so the default sort of zeroed out struct for cancellation token just happens to be a cancellation token that will never trigger cancellation. And so I can just treat it as any other cancellation token. And so I go forward then and I say, all right, well, what in here wants to be canceled? I could imagine maybe I want to cancel pick single file async, but it turns out the user would actually have no way. The user would have no way to signal that they want cancellation while that pick single file async is running because it's a full screen UI. It actually has its own notion of canceling. There's a cancel button on it, right? So I don't have to worry about some ambient cancellation in my UI having to force that to close. So I don't have to handle that one. But once the user's hidden the dialog, then we have to go open the file that they selected. And maybe between when they hit enter and they opened it, it's going to take a while because it's over the network or the thing was detached. And so I want to be able to cancel this also. But we saw there was a parameter on getAsync. There's no parameter here on openAsync. And this is one of those few remaining differences that's there between the Windows runtime and the .NET async world. And it's the fact that Windows runtime objects here have that first class notion of cancellation. You see I'm dotting into that operation object I get back, and you see there is a cancel method. And so the way you cancel in the WinRT world is you take the operation object you got, and you call cancel on it. And so again, it was a different API design choice. They have that on the operation object itself. But what it means is that I would have to now start doing that bookkeeping. If I cared about canceling this particular operation, I have to remember if it was current and so on. And so what I would rather do instead is convert this to a task. And you'll see that, remember I called as task before, it just wraps it as a task, that's fine. But there's actually an extra overload of as task that accepts a cancellation token. And what this will do is it sort of provides that virtual parameter that I wish the method had. Right? I call as task, and now I can specify cancel here. And it's as if I had a cancellation token parameter on OpenAsync. It's going to do all the plumbing to register the token and remember that so if cancellation is requested, it's going to go say, oh, you requested cancellation, I'm going to call the cancel method on that operation. It's abstracting over that and keeping that plumbing hidden from me. I get to think of it the same way. I have a cancellation token coming in, I hand it off to the people I call, and I don't have to worry about wiring up the rest of that plumbing myself. And so I've done that here. And let's say this is the operation that actually triggers cancellation. Well, if it is, what do we want to happen? Well, cancellation is a form of exceptional control flow. Right? Any given thing could be happening where, at the given time, that might want to be canceled. I have maybe 5 or 6 different places here that you could imagine canceling. In that case, I really just want to handle it in one place. I want control to bubble back out of there for me to abort the process that's ongoing and for me to handle the cancellation centrally. And so, again, we handle cancellation as an exception, and that lets us treat it exactly the same way we treated the error exceptions that we had. Let's say this triggers an exception, a cancellation exception starts bubbling out from here. Well, it's naturally captured in the task of storage file. It captures that exception, surfaces it again. When I go back up here, we're going here, we get the source image async. We're awaiting it down here. And let's say this was now in the accepted state because there was a cancellation exception. This is now going to throw that exception. And so we can now just make a catch block that's going to catch cancellation exceptions. So we catch operation canceled exception. And what we want to do in the UI when someone cancels is we just want to kind of blank out the UI, put them back in the state where they started. So the way we do that here, I'm just going to say item list view dot selected item equals null. So because of all the data binding, if I unselect the item that's there in the list view, it's going to clear out the right side of the UI. And so the one last thing we want to do then is actually trigger the cancellation. And this is why we put that cancellation token source out at the class level, and so we have access to it to see, hey, what's ongoing at the current time. And so I say here, if CTS is not null, meaning if there is something worth canceling going on right now, go ahead and say cts.cancel. And so this is going to say, I have something to cancel, I'm going to go ahead and cancel it. I'm now going to also mark that there is nothing to cancel. So if we came back into here again, we wouldn't try to cancel it a second time. And that should be it. If I run this now, I hit flower. I choose my image. Those network images are downloading in the background. I hit open, and now while the mosaic is calculating, I can hit back, and I was able to cancel, and it clears out the right side of the UI. And there, it happened to be calculating mosaic, but let's say the download didn't finish, or there was an issue opening the source file, and it was taking a while. No matter what thing happened to be running, I would have handled that exception, that cancellation exception, in precisely the same way. I would have caught it, it bubbled out, I went to my catch block, and I moved on. And so we talked about interacting with this ongoing in-flight operation. Cancellation is one reason you'd want to do that. That's when you want to send data to something that's ongoing. But you also potentially want to receive data from something ongoing. And the case for that is for progress. And so we also in .NET have a first-class notion now of how do we handle progress for operations that are in flight. And it's this iProgress interface. And so methods that can give you back progress notifications as they go through their operation will take an iProgress, and you can pass an implementation to that. It'll notify you of stuff. Again, in WinRT, they have a first-class notion of progress. So just like there's a cancel method on async operation, I think they call it async operation with progress. Right? There's a cancellation method in all async operations, but if you have an async operation with progress, then it'll have a progress delegate, too, that you could assign to and say, hey, whenever you have progress, call into this delegate and give us progress notifications. It's a different model. And what we do with as task, we also have an overload for those WinRT operations that takes an iProgress. and it'll do all that internal plumbing. It'll sign up its own delegate there. When it gets those notifications, it'll resurface them through URI progress. And then you get to think of it just the same way you do for .NET types. And so you can kind of tell, right? We called into a lot of WinRT operations there, and basically all the WinRT stuff that we were doing, we were interacting with it through async APIs. And this is, again, because of that huge bet they want to take on asynchrony so that you can make responsive UI apps. They don't want to leave you the hooks that you're going to fall into the pits, right, and say, oh, I'm going to call this method. You don't realize it's going to take a while. Maybe it doesn't take a while in your dev box, but it does take a while out in the wild on someone's tablet, and then the app isn't responsive. So they're keeping you on the rails there of saying, we're going to make sure that you're doing operations on the UI thread that are responsive. But at the same time, it could complicate the programming model. You could get into those kind of 7-level nested lambdas. You could start to feel that pain of having to compose async operations. But we've done the work in the languages so that the await keyword in VB or in C# can help you make those async APIs as simple as possible to consume. And hopefully, in most cases, it should feel as simple to consume as it is when you're calling synchronous APIs. And the goal, if we did everything right, is that you have no more callbacks. All right. That's it. Thank you.